NASA has finally lifted its long-standing silence regarding the latest discoveries from the James Webb Space Telescope, JWST, focusing on the planet Mercury. This groundbreaking revelation, previously hidden from the public, has captured attention worldwide, particularly regarding Mercury's volatile surface and unstable atmosphere. These findings have sparked significant interest and speculation for years, offering a harsh yet fascinating look into the limits of planetary evolution. The discoveries made by the JWST are truly revolutionary, suggesting the possibility of advanced processes that could reshape our understanding of Mercury and even our solar system's history. What exactly has NASA uncovered in its investigation of Mercury? Let's dive into this remarkable discovery and explore how the JWST has uncovered new insights into the closest planet to the Sun. Despite Mercury's close proximity to the Sun, which should theoretically render it a lifeless planet, scientists have long expected that this small rock, just slightly larger than Earth's moon, would have been battered by the Sun's intense radiation, potentially leading to its destruction. The temperature variation between the planet's two sides reaches approximately 1,100 degrees Fahrenheit, making it an incredibly inhospitable environment. However, Mercury has proven to be a complex and puzzling world, full of surprises that scientists previously underestimated. New data suggests that Mercury is much more than just a dry, barren rock. Mercury, one of the 5 planets visible to the naked eye from Earth, has been known to humanity for millennia, though the exact date of its discovery is unclear. It was likely observed by ancient civilizations long before written records were preserved. The planet was named after the messenger god Mercury by the ancient Greeks and Romans, who were among the first civilizations to study it. Mercury was associated with the Greek god Hermes, believed to be the divine messenger, due to the planet's swift movement across the sky. Through the centuries, our understanding of Mercury has evolved, with astronomers making significant breakthroughs. In the early 17th century, Johannes Kepler made a crucial discovery by observing that Mercury's orbit around the Sun was irregular, rather than elliptical. With the advent of new tools and techniques in the 19th and 20th centuries, more important discoveries followed. 2 missions have already visited Mercury, with the third, Bepi-Colombo, scheduled to arrive in late 2025. These missions, conducted by Japan and Europe, have been instrumental in clearing up many early misconceptions about the planet. Mercury may be small, but it packs a significant punch. Although its diameter is just slightly larger than the Moon's, Mercury is more than 3 times as massive as Earth's satellite. In fact, it is the second densest planet in our solar system behind Earth. This extreme density is due to its large iron core, which accounts for about 60% of the planet's volume, in contrast to Earth's core, which only makes up about 15%. This peculiar internal structure has sparked theories about Mercury's origin. One possibility is that the Sun's solar winds may have stripped away the planet's outer layers during its early history, or that a massive impact may have removed part of Mercury's crust, exposing its denser interior. The first mission to visit Mercury, Mariner 10, discovered that the planet has a magnetic field, a finding that surprised scientists. Mercury's small size led researchers to believe it would have cooled quickly, causing its interior to solidify and its magnetic field to disappear. However, the existence of a weak magnetosphere suggests that part of Mercury's core is still active. The planet's magnetic field is roughly 100 times weaker than Earth's, but its presence indicates that Mercury is still in the latter stages of its formation, slowly evolving toward becoming a dead planet like Mars. In the 2010s, the second Mercury mission, Messenger, revealed that the planet's magnetic field is peculiar. Its south magnetic pole does not align with the geographic South Pole, but is instead located nearly at the center of the planet. According to Antonio Guva, a planetary geophysicist at Rome Sapienza University, this magnetic field offers a window into Mercury's past, providing insights into how the planet's rotating core has slowed down over billions of years. To further investigate Mercury's secrets, Guva's team will make use of the ongoing Bepi-Colombo mission. Mercury's exosphere is another area of intrigue. The planet has such a thin atmosphere that it does not qualify as a true atmosphere. Instead, it is referred to as an exosphere, a rarefied gas layer that registers very little pressure. This exosphere is composed of atoms blasted off the planet's surface by solar radiation and cosmic rays. Research into Mercury's surface and internal composition benefits from comparisons with laboratory experiments simulating conditions found on Mercury, offering valuable insights into the planet's geology and mineral composition. In the coming year, orbiters will closely examine Mercury's mineral composition, surface features, and internal structure. By comparing these new findings with data from previous missions, scientists aim to determine whether Mercury remains geologically active, possibly experiencing surface cracking due to material dissipation. These observations will provide further clues to Mercury's mysterious origins and also offer a broader context for understanding the development of our solar system. Understanding why Mercury is so dense, with such a large core, is critical to our understanding of the formation of our solar system's first planet. Meanwhile, recent observations of the exoplanet 55 Cancri E using the James Webb Space Telescope have revealed a carbon-rich atmosphere, offering solid evidence that rocky exoplanets can indeed sustain atmospheres. These findings not only enhance our understanding of exoplanetary environments but also help refine our knowledge of planetary processes across the universe. In 2025, the upcoming Colombo mission aims to build on the findings from the Sailor 10 mission, revealing deeper insights into Mercury's geological history, surface features, and volatile elements. A key area of focus is the planet's magnetic field, which is notably strong for a planet of its size and proximity to the Sun. Unlike Earth's global magnetic field, Mercury's is much weaker and misaligned, with its magnetic north pole shifted from its geographic north pole. Scientists believe this field is generated by a dynamo process in Mercury's partially liquid iron core. However, the precise mechanisms supporting this magnetic field remain a subject of ongoing research, despite the planet's small size and slow rotation. Understanding Mercury's magnetic field is crucial for gaining insights into its internal structure and evolutionary history. Mercury's surface is marked by a variety of geological features, including impact craters, smooth plains, and unique hollows. Impact craters, formed by collisions with asteroids and comets, are abundant and provide valuable clues about the planet's impact history. The smooth plains, believed to have resulted from volcanic activity early in Mercury's history, suggest that the planet was once geologically active, with molten rock flowing onto its surface. These volcanic features indicate that Mercury's interior was once hot enough to melt rock, similar to Earth's geological processes. In addition to impact craters and volcanic plains, Mercury also displays peculiar hollows, irregular depressions with bright interiors. First observed by the Messenger mission, these hollows are thought to form through a process involving the sublimation of volatile materials, possibly due to intense solar radiation. The discovery of these features challenges previous models of Mercury's surface evolution and raises questions about ongoing geological processes on the planet. Mercury's exosphere is another intriguing aspect of the planet, consisting of a thin, dynamic atmosphere composed mainly of oxygen, sodium, hydrogen, helium, and potassium. Unlike Earth's dense atmosphere, Mercury's exosphere extends far into space, made up of particles ejected from the planet's surface by solar wind and micrometeorite impacts. The exosphere is continuously replenished by the release of gases and particles from the surface, and interactions with the solar wind play a critical role in shaping its composition. Despite its extreme proximity to the Sun and scorching surface temperatures, Mercury has permanently shadowed regions near its poles where water ice and other volatiles can exist. The discovery of water ice, first confirmed by Messenger using radar observations of polar regions, raises fascinating questions about the planet's geological history and the delivery of volatile-rich materials over billions of years. Along with water ice, Mercury's surface contains other volatile substances like sulfur, potassium, and chlorine, which are integral to the planet's surface chemistry and atmosphere. These volatile elements provide clues about Mercury's formation and environmental conditions. In addition to shedding light on Mercury's own evolution, studying the planet also enhances our understanding of rocky exoplanets, planets orbiting other stars. Advances in exoplanetary studies, particularly through instruments like the James Webb Space Telescope, JWST, have revealed a wide variety of exoplanets with diverse sizes, compositions, and orbital characteristics. Rocky exoplanets, akin to Mercury, present unique challenges and opportunities for understanding planetary formation, habitability, and the conditions that may support life. The discovery of carbon-rich atmospheres on exoplanets like 55 Cancri e challenges previous assumptions about the limits of planetary atmospheres, particularly those located close to their parent stars. Future research and missions, including those led by the Colombo mission, will continue to unravel the mysteries of Mercury. These missions will provide unprecedented data on the planet's surface geology, internal structure, and magnetic field. Advances in space telescope technology alongside future missions will revolutionize our understanding of exoplanetary atmospheres, surface compositions, and potential habitability. By studying Mercury and other rocky planets, scientists aim to decode the fundamental processes that govern planetary development, evolution, and the possibility of life beyond Earth. In conclusion, Mercury remains a captivating world that continues to challenge our understanding of planetary science. From its magnetic mysteries to its volatile-rich surface and dynamic geological features, Mercury offers a unique window into the complex processes that shape rocky planets across the universe. As exploration efforts progress and new discoveries unfold, Mercury will undoubtedly play a key role in advancing our knowledge of planetary systems, which was discovered in 2004. Orbits extraordinarily close to its star, resulting in surface temperatures high enough to potentially condense iron. Initially believed to be too hot and too close to its star to have an atmosphere, new findings from the James Webb Space Telescope, JWST, challenge this assumption. The data reveals that 55 Cancri e is surrounded by a carbon-rich envelope, a vaporous layer unlike what scientists had previously anticipated. Initial evidence of this atmosphere came from a temperature anomaly detected by JWST's mid-infrared instrument. Specialists, including Murray and his team, observed heat emissions from the planet's dayside, predicting temperatures of around 4,000 degrees Fahrenheit. Surprisingly, they found a lower temperature of approximately 2,800 degrees Fahrenheit, suggesting that heat is being transferred from the dayside to the nightside, likely due to atmospheric circulation. Further observations using the JWST's near-infrared camera revealed the presence of gases like carbon dioxide and carbon monoxide around the planet's surface, where liquid rock exists. Despite its proximity to its star, which would usually strip away an atmosphere due to solar winds, these findings suggest that the planet's atmosphere may not have been lost since its formation. Instead, scientists propose that 55 Cancri e's carbon-rich atmosphere is continually replenished by emissions from its interior, compensating for the loss of atmospheric material to space. With the upcoming Child Colombo mission scheduled for 2026, researchers are hopeful that further studies will offer more insights into the conditions of this super-Earth and similar exoplanets, enriching our understanding of their atmospheres. The exploration of Mercury, the closest planet to the Sun, has been marked by significant discoveries and technological advancements. From humanity's first attempts to understand the planet through missions like Mariner 10 and Messenger, to ongoing efforts like the Child Colombo mission, our knowledge of Mercury has expanded significantly. Launched in 1973, Mariner 10 was the first spacecraft to fly by Mercury, providing the first close-up images of the planet. It completed 3 flybys and captured detailed pictures of about 45% of Mercury's surface. Among its key findings were evidence of Mercury's magnetic field and its heavily cratered surface. Following Mariner 10, the Messenger mission, launched in 2004, became the first spacecraft to orbit Mercury. It arrived in 2011 and spent more than 4 years gathering extensive data on Mercury's surface composition, magnetic field, and surface history. Messenger's discoveries transformed our understanding of Mercury, including evidence of past volcanic activity, tectonic movements, and water ice in permanently shadowed craters. The Child Colombo mission, a collaboration between the European Space Agency (ESA) and the Japan Aerospace Exploration Agency (JAXA), aims to further our understanding of Mercury. Launched in 2018, the mission is a dual spacecraft endeavor designed to study Mercury's structure, magnetic field, and surface conditions in greater detail. It consists of 2 spacecraft, the Mercury Planetary Orbiter (MPO), which will focus on Mercury's surface and composition using a range of instruments including cameras, spectrometers, and a laser altimeter, and the Mercury Magnetospheric Orbiter (MMO), which will investigate Mercury's magnetosphere and its interaction with the solar wind. This mission will help scientists understand how Mercury's magnetic field has evolved over time and offer new insights into the planet's internal and external processes.